As we have seen previously, charges moving in a magnetic field can experience a magnetic force. Since a current flowing in a wire is just a collection of moving charges, then currents, and thus the wire, should also experience a magnetic force when in the presence of a magnetic field. Consider the situation shown in the figure, where a current-carrying wire is placed between the poles of a magnet. When the direction of the current I is as shown, the moving charges experience a magnetic force that pushes the wire to the right in the drawing. The direction of the force is determined in the usual manner by using right-hand rule 1, with the minor modification that the direction of the velocity of a positive charge is replaced by the direction of the conventional current I. If the current in the drawing were reversed by switching the leads to the battery, the direction of the force would be reversed, and the wire would be pushed to the left. The following clip shows a physical demonstration of the effect of the magnetic force on a current-carrying wire. Just as in the figure, we have a loop of wire that is free to swing back and forth. The bottom of the loop is suspended in the magnetic field of a horseshoe magnet, with its north pole on the bottom and its south pole on the top. Thus, the magnetic field points in the upward direction. A current is turned on in the loop in the direction shown, and right-hand rule 1 shows us the direction of the force on the bottom of the loop. If we switch the battery connections, then the current runs through the bottom segment of the loop in the opposite direction. Applying right-hand rule 1 again, we see the force should point in the opposite direction, and when we check it experimentally, that is indeed the case. As we will see, the magnitude of the force is directly proportional to both the current in the wire and the magnetic field. For large currents in fields, this force can be significant. Even for the small demo we showed here, the magnetic force is strong enough to quickly push the loop in the direction of the force. When a charge moves through a magnetic field, the magnitude of the force that acts on the charge is F equals delta Q VB sine theta, where theta is the angle between V and B. Consider the figure now where a wire of length L carrying a current I is located in a magnetic field B, where theta is the angle between I and B. We can take the equation above and multiply and divide it by delta T. Doing some rearranging, we get the following, where delta Q over delta T is the current and V times delta T is just the length L of the wire that's in the field. This provides the relationship for the magnetic force on a current-carrying wire in a magnetic field. And just like for a single charge moving in a magnetic field, the magnetic force on a current-carrying wire will be maximum when the wire is oriented perpendicular to the magnetic field.